Hey guys, and welcome to another Further Stats 1 revision video. Today we're going to take a look at the chi-squared test and also goodness of fit. So this is quite a lengthy chapter, and it's probably going to end up turning out to be quite a long video. But this has definitely been one of the most requested topics I've had from the Further Maths spec. So hopefully this helps anyone who's requested it. So yeah, let's jump straight into it. So the first question here, taken from the mixed exercise 6, question 7. We've actually got a chi-squared test here. So let's have a look at what we've got. So we've got a group of 50 males, 50 females, and basically we're kind of testing whether there's any evidence of an association between gender and passing the driving test at first attempt. So the first thing with any of these questions, where you're doing a hypothesis test, obviously let's write down our hypotheses. So one of the big things here, I might be kind of short of room, but let's see if we can do it. So H0, we're going to say that there is no association, so no association. So there is no association between gender, because that's what we're investigating, between gender and passing first time. So passing first time. Probably should mention that it's a driving test, but I'm just being a bit lazy. So then your H1, it's pretty much the exact same, but this time there is an association. So I'm just going to write out there is an association. You should still write out the rest of it, but just to save time, you would write all the rest of it. Okay, so exact same, but this time there is an association. So we've got our hypotheses. Whenever you're doing one of these kind of questions, we always need the expected values. Now, for chi-squared like this, what we actually do here is we're going to write down our totals. So if I actually change this to a black pen first, what I've got is a total. So total. Well, all you do is just add these, right? But obviously, these are your males, and we're told there's 50, so your total will be 50. Same again here, 32 plus 18. That'd be 50 as well. Add these together now. So 23 plus 32. So this would be my next total here. This is the total that passed. So 23 plus 32, that's 55. And then 27 plus 18, that'd be 45 there. And again, they should add up to 100 because there were 100 people in the survey or whatever it is. Survey. So 100 people there. Obviously, we should get 100 here again. So everything's good so far. Now, to actually work out your expected values here, so what I'm going to do, I'm going to set it up as a table, but I'll do a couple just to show you kind of the method for it. So what I'm going to do is I'm going to write down my observed values and then my expected values here. Okay. So obviously make sure yours is a little bit neater than mine. Mine's a bit scruffy, but you know, you get the idea. So what do we have? We have 23 were observed, 27 were observed, 32, and 18. Okay. So now we just need to work out the expected values for the corresponding. So this 23 here corresponds to 23 males passed. The 27 is 27 males failed. The 32 is that 32 females passed, and then the 18 is that 18 females failed. So how do I work out this expected here? Well, so this is for the males that passed. So we're along this row here because it's males. So the total there is 50. So you take your row total, which is 50. And then you times it by the column total, which is 55. So 50 times 55. And then we divide that by the grand total. So the grand total here is 50 males plus 50 females, so 100 in total. Okay. Do that on your calculator, and what you get here is 27.5. Okay, so that's 27.5. If I do the same for the 27 here, just so you can kind of see the method again. So we're along this row, because this is for the males that failed. So 27, the 50, because we're on that row, so 50. We're along this column now, the failed column, so that's times by 45. And then again, we divide it by the total, so 100 again. And again, that'll give you 22.5. Now I'll just write in the other two. What you have to get is you just get the exact same here. So again, 27.5 and 22.5. Okay, so Then we're at expected values. So now once we've got the expected values, now we can actually go about calculating the test statistics. So there's two different formulas you can use. The one I generally would use is just the summation of my observed minus my expected squared divided by the expected. Okay, you just need to sum this up. So you need to work out each one individually. So for example, if you do 23 minus 27.5, square that and then divide it by 27.5, what you'd get here is 81 over 110. Okay, so I'm going to sum this up. Again, I've done all these, before actually recording the video, but just do it yourself just to make sure you can actually get the same values. But what you should get is 81 over 110 plus 9 over 10 plus 81 over 110 and then 9 over 10 again. Okay, add all these up now, and what you should get here is 3.27. Okay, so that's my test statistic. Okay, so that's kind of the good news. We've got the test statistic. Now we just need the chi-squared value that we're going to compare it to. So first we need the degrees of freedom, so that's V. Well, for a chi-squared test like this, you need to look at how many rows you've got and how many columns you've got, and we subtract one from each and then times them together. So we've got 2 rows and we've got 2 columns here. So that's 2 minus 1 times 2 minus 1 there. Okay, and obviously 2 minus 1 is 1, times it by 1 again. We're just going to get 1, right? So I've got 1 degree of freedom here. So now using my chi-squared table, so just use your formula book for this, nothing special. So using chi-squared tables, I'm just looking up here now in the table. So at the 10% significance level, because it's 10%, at 10%, this gives you 2.705. Okay, and now all we do is compare our test statistic to our chi-squared value here. If this value is bigger, then we would reject H0, okay, which it is. So 3.27 is bigger than 2.705, so if we do it all the way up here just to finish, 2.705, therefore we reject H0, and we can say there is evidence at the 10% significance level. To suggest, well, basically that there is an association. To suggest an association. This is what I hate about these questions. There's so much rhyme. There's an association between the gender and passing first time. Okay, so I'm not going to write out coming in a room, but that's what your association's between. Okay, and there I have it. So that's just all that for 6 marks. This is kind of why I hate this topic. There's a lot of working that goes into it. But mathematically, there's nothing too complex in here. So, if you can get the methods down, you should be okay. But that's the first question done, and then we've got the 6 marks there. So next question is from exercise 6C, question 4. So the first part, and this is quite a common kind of, building up to the main part of the question, is where it'll ask you to explain why there's a certain number of degrees of freedom. So in this case, we're told that there's 4 degrees of freedom. We're asked to explain why. And then part B, we've got to perform the test at the 5% significance level. So what we've got to look at here is we've already been given the expected value, so it's kind of a nice one. They've already done most of the work for us. We've just kind of got to work out why there's 4 degrees of freedom. Now, so if we take a look at this one here, question 4A. For a question like this where you're kind of comparing unobserved data and whether it fits the distribution, so essentially goodness of fit, what we do here is the number of columns, and then we would subtract it by the constraints. So in this case, the only constraint is the total, okay? Well, what we've actually got here is we've got 1, 2, 3, 4, 5, 6, 7. We've got 7 columns. If we subtract 1, that'd give us 6. So, and obviously, the big hint is looking at your expected values. Remember, if your expected value is less than 5, you have to pool, right? So I've got the greater than 5, which is 1. I've got the 5, which is 3, and then I've got the 4 dogs is also expected at 4. So we need to do a bit of pooling there. So we'll kind of work from right to left, so you're going across this way. So the 1 would pool with this one here. So that'd give me 4 expected, and then we could also pool it here. So what I'm going to do, I'm just going to write down the table again, just so we can actually see it. In fact, actually, I won't kind of do that. What I'll just do is I'll write in the last one. So what you'll actually get here is the last column here will be greater than or equal to 4. We will have had 4 plus 6 dogs, so that would have been 10, and then add another 7, so that would have been 17 observed. And then we would have also had the expected, which again, just add them up. So 1 plus 3 is 4, plus another 4, that gives us 8 there, okay? So what we've actually got now is 1, 2, 3, 4, 5, okay? Because we've got greater than or equal to 4 there. So we've got 5 columns, we've only got 1 constraint, the total, so therefore, once you do 5 minus 1, you get 4. So, pooling, 4, 5, and greater than 5 together gives 5 columns, and we have 1 constraint. So therefore, 5 minus 1 gives us 4, which is our degrees of freedom there. Okay, so that's your degrees of freedom. So that's part A done. Somehow I've took up most of the screen just for that one part. So we'll quickly clear this and then jump into the rest of it. So now for part B, we actually have to perform the test. So 5% significance level. Well, again, start with your hypotheses. So H naught, we're going to say that the data is drawn from the expected distribution. Or you could say it fits the distribution. And then obviously your H1 is just the opposite. It doesn't fit the distribution. Is not drawn. Okay, so the rest is just this here. So the data is not drawn from the distribution. Okay, so them are our hypotheses. Now we need to use the formula again. So we need to find the summation of observed minus the expected squared divided by the expected. Okay, so you need to do it for each one here. So for example, do 45 minus 55, which will give you 10. Square that, or it'll give you minus 10, sorry, square that, you get 100, and then divide that by 55. Okay, so what I'll do is I'll write down all the values, and then you just need to add them up together. So obviously you should get the same as me here, so this would be 20 over 11, and obviously you just keep doing the same. So 19 minus 20, which will give you minus 1, square that would be positive 1, and then you divide that by 20. Okay, so that'll give you 1 over 20, for example. So obviously if I just write the rest down, that you should get 1 over 10, 1 over 7, and then 81 over 8. Okay, adding all them together, we get 12.236. Okay, so that is the test statistic. So now all we need to do is write down our degrees of freedom, which we've already been given, is 4. So V is 4. So using that at the 5% significance level, we can work out what we need to compare this to. So this is the chi-squared value for 4 degrees of freedom at 5%. What does this give us? You read across from your table, you just get 9.488. So again, we compare the test statistic to the, well, basically this value here, my chi-squared value. If it's bigger, we reject. If it's smaller, we accept. Well, 12.236 is clearly bigger than 9.488. So, again, we reject H naught. So how can we describe it? Basically, we've got evidence at the 5% significance level. That the data does not fit. The expected distribution, or it doesn't fit this distribution. Okay, and that's your 7 marks there for that one. Next question is actually taken from the old spec for the Edexcel for maths modules. This was S3, okay, so it's pretty much the last module. So 10 marks for it. The first part, you've just got to work out the missing expected frequencies. And then part B, we're just testing whether or not Linda's claim is supported. And basically, Linda's claim is that, what is it? I've not read it myself. Okay, so basically she's just testing whether, it's equally likely to come at rest at any point. So what we've actually got here would be a continuous uniform distribution, okay? If basically it can rest at any point and it's equally likely. So what we'll do is we'll do it up here to start with. So question 2. So we've actually been given 2 of the expected frequencies. So if we see if we can kind of figure out using that how to work out the rest. So for the angle between 0 to 45 degrees, we're told that the expected frequency is 12.5. Well, you've kind of got to think about how this question will actually work. So for the expected frequency A, if it's equally likely to land on any of these points between 0 to 360 degrees, well, what we'd expect, and because she spins it 100 times, what we'd expect is that would be 45 possible values, 0 to 45. So that's 45 out of 360. But she spins it 100 times, right? So it's going to be 45 divided by 360 times by 100. Okay, so that's what it would have been for this one, but it's also the case for this one as well, because 90 minus 45 gives you 45 as well. Okay, perform this on your calculator, which obviously it would just be the same as this anyway, so you can double check it if you want, but you will get 12.5 as well. Doing the same here now for this one, but just be careful. This time we're going between 90 to 180, so B is, well, it's going to be 90 divided by 360 and then times by 100. If you can spot it straight away, you can just double this value here, okay? Because this is 90, which is double the 45, so this has to be double as well, okay? So that'll give you 25 for B. And then finally, doing the same for C here. This time it's between 180 to 315, so you just need to subtract 180 from 315. So doing that, you'd get 135 possible out of 360. Times it by 100. So what do we get in total? So we get 37.5 there. Okay, so them are my expected frequencies. So now we've got the expected values. Let's just go about doing the test. So again, 5% level of significance. So H naught here now. So this time we're going to say, so because it's equally likely to come to rest at any point between 0 to 360, it's a continuous uniform distribution. So continuous uniform distribution. Oops, distribution is a good fit. And then your H1, again, just the opposite of this. It would not be a good fit, so is not a good fit. Okay, so that's your H0 and your H1. So we've got the kind of the basis of this question. Let's have a go at tackling it now. So same as always with these questions. Again, we've already got the expected values, so now we can just jump straight into calculating the test statistic. So the summation again. So I'm getting tired of writing this formula down. So it's the observed, that's the expected squared, divided by the expected. And again, just like we did with the last one. So for example, the 18 minus 12.5 squared, and then divide it by 12.5. So I'm not going to write these out, because they're pretty just basic calculations, but what you should get here is 121 over 50 plus 49 over 50 plus 49 over 25 plus 289 over 150 plus 169 over over 50. Okay. So now just add all these up because we need to sum it. So that'd be 10.67 there. So now we need to work out our degrees of freedom. So how many columns do we have? We've got 5 to start with. quick check of the expected frequencies, make sure none are less than 5, which they clearly aren't, so therefore we don't need to pool anything. So we've got 5 columns. The only constraint we have is the total. So in this case now, V is equal to 5 minus your 1 constraint, which is giving us 4 in total there. So now we just need to work out the value we're going to compare it to here. So it's a chi-square test, 4 degrees of freedom, and at 5% here. So what will that give us? Well, if you check that on your formula book, it'll be 9.488. I can't remember if that was the same as the last one. I think it might have been. So yeah, you'll get used to these values eventually. So again, comparing whether this is bigger or smaller than my value here. And again, it's bigger. So again, we're going to reject. I promise they're not all rejects. So reject H naught. Evidence at 5% significance level. To suggest. Basically, you can just say that Linda's claim, basically, that is not correct. So to suggest that Linda's claim is incorrect. And there we have it. Okay, so another quite big question out of the way. 10 marks for that. Like you see, they are a lot of marks, generally speaking. So this one is actually a dead brief one. I don't think you necessarily get tested on something like this individually, but it's important that you understand why these things work and the intricacies of it. So the question tells us that an investigation is going into a health centre. It's a 5x3 contingency table, and it's at the 5% significance level. So we're just asked to work out the degrees of freedom and the critical region appropriate for this test. So if it's 5x3, think like what we've just been doing for our contingency table. So remember, contingency table is just what we're doing for a chi-square test. Well, we do the rows minus 1 times by the columns minus 1. So for V here, so that would be 5 minus 1 times by 3 minus 1. 5 minus 1 is 4. 3 minus 1 is 2. Okay, and 4 times 2 gives us A. So we have 8 degrees of freedom. Now we need to consider the critical region that's appropriate for this test. So what we've got to do here now is just use our formula book, read across on the chi-squared tables for our value. So this is a chi-squared test here. We've got 8 degrees of freedom at the 5% significance level. Read across your table here. So all you've got to do is here, make sure you actually read it correctly. So you get 15.507. But be careful, we need to actually define the critical region here. So the critical region is where would we reject this. And remember, we'd actually reject this if chi-squared, our test statistic, is bigger than this value. So it's bigger than 15.507 there. Okay, so you just got to be very careful for that. It's only bigger than, not greater than or equal to. Okay, so just be careful for that little point there. So another chi-squared question here. Very kind of standard question, just comparing two kind of grades, usually the case or something to do with drugs. So question 4. So don't be put off by the 0.05 significance level, just a 5% significance level. Okay, so 5%. Like any hypothesis test here, we need to define our hypotheses. So H0. So remember, for a chi-square test, your H0 starts off as being no association. So there is no association between English and maths results. And then obviously for your H1, make sure you're defining it as basically the opposite, so there is an association. And then just copy the rest down there. Okay, so then your hypotheses there. Here now we need to work out the expected frequencies like we did, I think it was the very first question. So expected frequencies. So we do it over here. So consider like we did before. So you're going to have your totals again here. So am I better doing this in another table? What I'll do is I'll write my individual totals down. So if I just do it dead quick here, so change my pen. So you're going to have your totals here. So if I do it on my calculator just to save time, so for example, dead quick, you had 17 plus 28 plus 18, that gives me my total there. So that's 63. 38 plus 45 plus 16, that'll give you 99. And finally, your last one, 12 plus 12 plus 14, gives you 38. We'd also need the column totals, so 17 plus 38 plus 12, that's 67. That gives me 85. And finally, for my very last one, 18 plus 16 plus 14, that gives me 48. So now it's dead easy to work out your expected frequencies here. Consider like we did before. So it's going to be the row total times by the column total divided by the grand total here, which is 200. So, for example, if I want the expected for Maths A and English A, so that'd be this one here, I'm along this row total, so it's going to be, so this is Maths A, oh I'm in black. So, Maths A, and then English A. Well, that's going to be 63. And then we're along this row here as well. So it's 63 times 67 divided by 200. Put that on your calculator, and what you should get is 21.105. Let's work out another one just so you can see the method again. If I wanted, for example, Maths grade B and say English A, what would that be? Well, that would be 99 because we're along the Maths B row here. So 99 times English A, which is this column, so times by 67 again. And you always divide by 200 because that's your total here. Put that on your calculator and you'll get 33.165. And then finally one more. Say Maths grade C and English grade C. So this row here and then this column here. So Maths C and English C. So this is something you have to work out for each one individually. So what would that be? So it's going to be this bottom row here, so 38, times by this column total, which is 48. And then finally, divide by 200. Put that in your calculator and you'll get 9.12. So I've done all the rest of them beforehand. I'm not going to keep doing all of these, but just so you can kind of see the method, obviously you're going to have to do 9 of these in total. So what I'll do here, just to make room, is I will clear all this. If we do it over here, am I going to have enough room? This is quite a long part working. I would do my observed here, my expected here, and then just so I can do my test statistic. There. Okay. So my observed values was, if I go from left to right here, so 17, 28, 18. Same again across the next row. 38, 45, 16, and then finally 12, 12, 14. Okay, so I'm actually nearly running out of room. So my expected values, once you write them all down, once you work them all out, 21.105, 26.775, next one, 15.12, 33.165, 42.075. Okay, so I worked these out, I just got to keep looking. 23.76, 12.73, the last two, 16.15, and then 9.12. Okay, so now you just need to apply the formula again. Observed, 17 minus 21.105, square that value, and then divide it by the 21.105. So again, I've done all these before, recording the video. What you should get is 0.7985, 0.0560, 0.5486, 0.7049, 0.2033, 2.5344, 0.0419, 1.0664, and then finally 2.6112. Right, okay, we're nearly there. So now you just need to add these up. Remember, the test statistic is the summation of this. So therefore, add all them up on your calculator. What you should get is 8.565. Yeah. So now we need to work out the degrees of freedom. So remember, number of rows minus 1 times by the number of columns minus 1. So it's 3 by 3, so it's just going to be 3 minus 1 times 3 minus 1. So 2 squared essentially giving us 4 degrees of freedom. So now all you've got to work out is your chi-squared value. 4 degrees of freedom, is it 5%? Yeah, 5%. So check across the table. Again, it's the one we always come across, 9.488 there. So compare your test statistic to this value. So this time it's smaller. So this time we accept, okay? So finally got an accept one. Accept H0. Or you can also say that there's insufficient evidence to reject H0. So accept H0. Basically, we can say that there is no association. There's no association between whatever we're comparing, the grades, between grades at the 5% significance level. So there we have it. Okay, so it's at the 5%, 0.05. I think this is the very last question here, I hope. Yeah, the very last one, so it's quite a long one, but we're nearly there. So this time, we're testing whether or not a Poisson model is suitable, to represent the data, basically. So what have we got here? Well, the first thing that kind of jumps out at me here is that we're not given the value of lambda. So straight away, you need to be thinking about estimating that value of lambda. But first, like we always do, let's write down our hypotheses. So H0. So Poisson is a good fit, or it's suitable. And then H1, Poisson is not a good fit. Okay. So now we need to estimate lambda, because we're not given it in the question. So this will actually affect your degrees of freedom as well at the end, but we'll come to that when we get to it. So estimating lambda. Well, to estimate lambda here, our mean, obviously we just need to work out the average of basically our number of restarts with our frequency. So just like you would for basically your GCSE maths here. So lambda, well, that's going to be equal to 0 times 99, and then we're going to do 1 times 65. We're going to add all these together, and then we're going to divide it by the total, which is 200 in our case. So 0 times 99 plus 1 times 65 plus 2 times 22. And then I knew I write a room plus 4 times 2. And then we divide that by 99 plus 65 plus 22 plus 12 plus 2, which is our total there, 200. Okay. Do this calculation on the top. What you should get for lambda here is that lambda is 153 divided by 200, which is equal to 0.765. Okay. So now we can use this value of lambda here to work out our estimated values. Okay, so this is where having a graphical calculator will save you so much time. What I'm going to do for this next part is write down the actual method, but everything I calculated was using my graphical calculator. Okay, if you have to do it by hand, it's going to take you a lot longer. Well, to get our expected frequencies now, so calculating expected frequencies. Well, now we need to use the actual Poisson distribution. So what we're looking for here is the expected at 0, 1, 2, 3. And then when we get to 4, remember, it can actually be more than 4 restarts, right? So we're going to go greater than or equal to 4. So at this point here now, what I'm going to have is expected at 0. Well, that's going to be the probability that x is equal to 0 times by 200, because we're looking at it over 200 days, okay? So times by 200. Same again for E1. And the probability that x is equal to 1 though this time. Again, times by 200. So this 200 is common across all of them. Probability this time x is equal to 2. Times by 200. E of 3. X equal to 3. Times by 200. And then finally for the last one, just be very careful here. This time it's going to be the total 200 minus, I should have actually put it as, sorry, so it should be I greater than or equal to 4 there. Okay, so it's going to be 200 minus my other expected values, so it's going to be E3 plus E2 E1 plus E0. Okay, so I've not made any other mistakes, so that's all okay. So let's calculate, well, I've already calculated them, but this is why a graphical calculator will save you so much time. If you don't have the calculator, you're going to have to put each one of these in it individually by hand and start calculating it. For 6 marks, it becomes a lot more work than it actually should be. So if you don't have one, get a graphical calculator. Calculating these though individually, your first one should be 93.07. The next one will be 71.20. The next one will be 27.23. And then 6.94. And then it's going to be 200 minus the sum of these. So 200 minus the sum, which is 198.44, which comes out as 1.56. Okay. Now we just need to look at our expected values. Do we need to pool? And we do need to pool, okay? This 1.56 is less than 5. None of the others are less than 5, but just this 1.56. So we're going to have to do a bit of pooling. So if I draw kind of like a table out again, I've got my observed here, my expected here, and then just kind of like I did before, I'm going to write down how to get my test statistic. So minus the expected squared. Okay. So now we've got this, now we can actually just start working everything out. So I've got, so this is for 0, 1, 2, and 3, and this is greater than or equal to 3, okay? So my table is terrible, make sure you use a ruler in your exam. It's a bit messy, but yeah. So the observed at 0 was 99, the observed at 1 was 65. At 2 is 22, and then greater than or equal to 3, it's going to be 12 plus 2, so 14 there. Okay, my expected now, so that's 93.07. It's going to be a bit all over the place. 71.2, 27.23, and then finally to get your last expected value, 6.94 plus the 1.56 there, which will give you, I won't lie, I missed to do that calculation, so if I do it now, it's going to be 6.94 plus 1.56, so you get 8.5 there. Okay. So now, just looking at your values, again, I've done all these by hand, but again, just make sure you can do it, 99 minus 93.07, square that value, and then divide it by 93.07. So what you should get here is 0.378, 0.539, 1.00 to 2 decimal places, and then 3.55 here. Okay, so basically we can get the test statistic, so that's going to be the sum of these values here, which is, I don't know if I put it down, I didn't write it down, so again, I missed this question out quite a bit, so let's work it out. So 0.378 plus 0.539 plus 1 is 3.55. So that gives you 5.467. Your critical value now, well, before we can work out our critical value, we need to get our degrees of freedom. So V, how many columns do we have? We've got 1, 2, 3, 4. Normally, we only subtract 1 off here. That's very common, which is usually total. But this time, we actually subtract 2 off because we've had to estimate lambda, okay? So it's 4 minus 2 here. So 2 degrees of freedom. So, getting your chi-squared value, so 2 degrees of freedom at the 5% significance level. That gives you 5.991. Okay, comparing your test statistic to this value here, again, it's smaller. So this time, we accept. So accept H0. Basically, there's insufficient evidence. Or basically, you could actually say, just to show you the other way you can write it, insufficient evidence to reject H0. To reject H0. This is the way you'll kind of see it across the mark schemes. But either way is absolutely fine. You can say accept H0, you can say insufficient evidence to reject H0 there. Okay, so I'll leave the final conclusion up to you guys to how you summarise that question. But hopefully this video's helped. Hopefully it's not been too long. I don't know quite how long this has been recording for. But if there's any mistakes in here, it's been quite a long one, so I've probably made one somewhere. Please let me know in the comments. But yeah, cheers guys.